For 26, we've got a trough that's being filled with water. It's a prism with a triangular base. The base, again, it's on its side, so the base is this triangle and this other triangle in the background here. Those are the bases of the prism. So then the water is being dumped in at 2 cubic feet per minute. Currently, the water is at 1 foot deep. And part A, they want to know if water is being pumped into the trough at 2 cubic feet per minute, how fast is the water level rising when it's 1 foot deep? 1 foot deep, sorry. So that's the situation we have already there. The volume of the water is the area of the base, which is a triangle, times the height of the prism. So as the water fills, I picture this thing in motion. The volume's changing, so it gets a variable. The base of the triangle, which is this thing right here, gets bigger, so that has to stay as a variable. The height has to stay as a variable, the height of the triangle, because that is this part right here going up and down. And then the height of the prism, the trough, is always staying at 12 feet. It's not changing as the water fills up. So that one I can put a constant in. So if I simplify this, I've got 6 base times height, and there's already a unit of feet attached to this thing. So I'm going to erase it, but know that it's there already. It's in that 6. So now when we take the derivative, we're going to end up with a dB dt and a dh dt, and we don't want to have both of those. We want to get rid of one of them. So they're asking at what rate is the height changing, so we need to keep h in there but not b. So the bigger triangle shows a relationship between the height and the base. It's a 1-to-1 relationship. So that means when the height of the water is 1, the width, the base across the top is 1. That means that B is equal to H. That's the ratio. So I can make a substitution, and I want all H's, so I'm going to substitute in H for B here. Simplify that, and I get 6H squared. Okay? So then I will take the derivative with respect to time. The rate of change of volume we know is 2 cubic feet. And that's cubic feet per minute. I won't put the per minute because it'll still stay there. We're still doing rates. When the height of the water is 1 foot deep. Okay, so that's a foot. Remember, this number out front already has feet in it. Okay, dh dt. So then when I divide, I'm really dividing by feet squared, and the feet cubed that's already over on this side ends up being feet. So it's 1/6 feet per minute. That's the rate of change of the height. I divided both sides by the 6 feet squared. That's part A. Part B is asking, where's the question? If the water is rising at a rate of 3/8 of inch per minute, so now they're telling us the dH dt is 3/8 feet per minute. The rate of change of the height determine the rate at which the volume is being pumped in. So I can still use this same related rates equation once I found it, but now they're telling me dH dt and wanting dV dt. The rate at which the water is being pumped in, that's volume. When the height is 2 feet. So remember, I go feet times feet, and this 12 already has a feet in it. So it's actually going to be feet cubed per minute. So I'm doing the 12 times the 2 times the 3 divided by the 8. So 12 times 2 is 24. 8 goes into 24, that's 3, so it should be 9 cubic feet per minute. That's the rate at which the water is being pumped.